This lecture in Climate and Earth 401 is the second lecture on vorticity, and in this lecture we will look at planetary and relative vorticity. Vorticity is a fundamental description of the fluid flow. It is as fundamental as wind. If you wanted to, you could start this course by defining a fluid in terms of its rotational and irrotational parts, and the rotational parts would be vorticity, and the irrotational parts would be divergence. The flow can be completely described by vorticity and divergence, and in the atmosphere, because the motion is often confined to be more strongly horizontal than vertical, the rotation is often in large-scale flow associated with the horizontal aspects of the flow, and the divergence, as we've seen in earlier lectures, is related to the vertical velocity. So this is an interesting aspect where the horizontal divergence leads to there being a vertical motion. Vorticity is also related to a concept called the circulation, where the vorticity is the measure of rotation linked to a point in a fluid, and the circulation is a measure of rotation around a closed circuit that encloses, say, that point. It's an area average. Circulation is an important theoretical construct, but we will not study it much in this course as I teach it. By definition, vorticity is the curl, del cross, the velocity field. And in this case, we've written the velocity vector as u sub a, where a is representing the absolute velocity, meaning that it is the velocity of the Earth plus the relative velocity of the atmosphere relative to the Earth. Vorticity is a measure of rotation in the fluid. Again, u sub a is the velocity in an inertial coordinate system. Hence, there is a contribution to vorticity due to the rotation of the Earth, and there is a contribution due to the motion relative to the surface of the Earth, which is called the relative vorticity. This is an important distinction to make. The difference between the vorticity due to the rotation of the Earth and the relative vorticity, which is the motion relative to a point on the Earth, or going back to our earlier lectures in the tangential coordinate system in which we use, which the vertical that we use in that coordinate system is the local vertical at whatever point we might be observing. Because in large-scale flows in particular, the flow is dominated by the horizontal motion, we're most interested in the vertical component of vorticity. Recall from the definition of vorticity, if the motion is in the xy plane, you might remember the skater who was holding her arms out. If the motion is in the xy plane, then the rotation is around an axis in the vertical plane. Using our vector notation, we would get this component by taking the dot product with the unit vector in the vertical direction. Hence, we are looking at k dot del cross u. In what plane is the motion? The xy plane. In what direction is the vorticity? The vertical. Relative vorticity is related to the velocity relative to our coordinate system that we are observing at on the surface, UVW. Hence, del cross u is defined as this vector here of dw dy minus dv dz, du dz minus dw dx, dv dx minus du dy. K dot, the vertical component of that, is often called zeta, and it is dv dx minus du dy. Here is a quantity that you should become very familiar with, dv dx minus du dy. This is the relative vorticity, zeta. The planetary vorticity is the vorticity due to the rotation of the Earth. If we go back to this figure that we looked at a number of times early in the course, where we talked about the rotation of the Earth and the importance of knowing the radius at any particular latitude. And what we were interested in is the rotation around the k unit vector of the local vertical. So here is our tangential coordinate system. Here is the vector of the orbital axis here. And what we want is the component of this in the local vertical. We see that this is maximum up here at the pole. It's 0 down here at the equator, and it's some value here in between, which is f, the Coriolis parameter, which is 2 omega times